With the talk on sensitivity versus plot sensitivity. So first I want to briefly remind you what we did last time. So we defined the sensitivity of a function, plot sensitivity. So f is a boolean function from 0, 1 to the n to 0, 1. Also the deterministic decision tree complexity, certificate complexity, the degree, and approximate degree. And last time we saw a lot of polynomial dependence between these parameters, except the first one, also except the last one. So basically today, the first thing I want to talk about is how to show the only remaining thing that I didn't prove. The plot sensitivity is bounded by the degree square. And then I will talk about how to get this Canyon Coutin's proof about the sensitivity is the plot sensitivity is bounded by basically an exponential function to the power of sensitivity. Now here, instead of 4 to the power of s of f, if you do it more delicate, in a more delicate way, you can get actually e. But that's the best we can get. Maybe you have a square root of sensitivity somewhere. Anyway, you will see the precise expression later. And then I'll talk about the different reformulation of this sensitivity and plot sensitivity conjecture. Okay, for those of you who were not here last time, I can say what's the sensitivity and plot sensitivity conjecture. So basically, you want to show that the sensitivity and plot sensitivity are polynomially related to each other. And if that's true, then all these parameters are polynomially related.
Did you show an upper bound on approximate degree?
Not yet. I still need to show this, but you will follow from here, because here this is not only true for the degree, but also true for the approximate degree.
But the others are upper bound on
Right.
approximate degree, you don't show.
But approximate degree is less than or equal to the degree.
Oh, sorry, upper bound. Yeah.
So basically, I will show that the degree is bounded by. I already showed degree is bounded by polynomial function. The plot sensitivity is bounded by this one, but we get a power of 6 or something. I think this is basically the most interesting proof in all this relation. Nissan is a Getty. Actually, there might be a parameter 2 somewhere. So, okay. Okay. Maybe I can write here. So we define the. Do I need to define the sensitivity? Okay, I will also do it. So the sensitivity of function f L point s is the number of coordinates I such that f of s plus ei is not equal to f of s. S plus ei is basically, think of s as the vector in the 0, 1 to the n, and ei is the unit vector. Then you basically you change the i's coordinate. And the sensitivity is the maximum local sensitivity. And similarly, we define the local block sensitivity is the maximum number of disjoint blocks of coordinates. B1 to Bt, for example, such that f of s plus bi is not equal to f of s. And there's examples showing that the plot sensitivity can be like k squared, and the sensitivity is like k, and that's the best separation that we know. And the conjecture is that the plot sensitivity is bounded by a polynomial function of the sensitivity. So here, so let's first suppose the block sensitivity is achieved at the point x, and also by the blocks B1 to B, let me just write B, okay. So in other words, we have fs plus bi is not equal to f of s.
By the way, can you give us an outline of this proof before? I mean, so what are the basic steps?
Okay, so basically the steps are the following. So first, we want to show that if f is fully sensitive, fully sensitive means the sensitivity of f is equal to the number of variables. F is sensitive, then we have the sensitivity is bounded by some constant times the degree squared. Well, I'm not saying that first we need to show this. I mean, first we can reduce this problem to this one.
I mean, so equivalently, if f is fully sensitive, it's proximate degree, then is at least root n.
Yes, it's also
So,
like some other
tight,
constant.
for example, for this, right?
For approximate degree, this is tight, but for the degree, I don't think it's tight.
Right, for approximate degree, it's tight for the OR function, right? Okay.
And but for the degrees, the best bound you can get is like log base 3 of 6 in the power. Yeah, this Cauchy-Lewis function.
The lower bound, you mean, about for a fully sensitive function, how large, how small its degree.
Yeah. Yeah. And after we do this, then we reduce it to the. Now we can assume that f is symmetric function. I will explain what symmetric function in a second. And then finally, from a symmetric function, we can get f is equal to the polynomial to the composed with basically the Hamming weight of the vector. And then we only need to work on polynomial. Then we can use Markov's inequality to get some. You can see in Markov's inequality I briefly mentioned last time, you have n squared, which is the square of the degree.
Wait, can you remind me again, Mark? Oh, okay.
I will anyway go to there.
Right.
And from there, you can get the bound. Okay. So first, let's see why, if we show this, then we can show this one. So we define g of y1 to yb to be the function where you add s with y1 times b1 plus y2 times b2 plus yb times bb. So g is also a function from, it's also a boolean function, but from 0, 1 to b to 0, 1.
What is the function g?
G is the function on the variables y1 to yb.
So it's f. What do you feed f?
So you have s plus y1 times b1. So if y1 is 0, then you don't take this block.
Oh,
If y1 is 1, you take it. You just change the block.
Okay.
x plus
So you're fixing a maximally.
Oh yeah, I already fixed the maximum number of blocks, and also, I mean, I take s, which maximizes this.
What is the times? N?
Where do we have times? Oh, times just mean you take b1 if y1 is equal to 1, and you don't take this set.
So
If
y1
y1 is
and
0.
y are selectors for which blocks you're going to end up
Yeah.
flipping. So for example, g is now a maximally sensitive function. I mean, it's a fully sensitive
Exactly.
What is
X
X?
is the point which gives the largest local block sensitivity. Now we can see, for example, G0, the all-0 vector, gives you f of x, right? And G1, if you take the others to be 0, then this is not equal. This is equal to f of s plus b1. Okay, now this definition is clear. Okay, and this is not equal to f of s because we are taking the sensitive blocks bi, and this is equal to g of 0, 0. And you can do the same thing if you have like any coordinates to be 1 and all the other coordinates to be 0. So basically, this implies that G is fully sensitive at the all zero vector. And now we only need to compare the degree of G with degree of F, but it's quite obvious that the degree of G is less than or equal to the degree of F. So if this is true, then we have what? We have the broad sensitivity of F is equal to the sensitivity of G bounded by some constant times the degree square of degree of G bounded by some constant times the square of degree of F.
So this bound is obvious, the degree of G less than or equal to the degree of F, right?
Oh yeah. Mm-hmm. And
It's just
you
the
can just see how
substitution-
when you
sorry,
apply this, you can see how these monomials in the expression changes. Right? You can never exceed the original largest degree. Is everything clear so far?
So G almost looks like an OR, but we would have to worry about what it looks like when we set two
Yes.
ones, for example, right?
Yes.
Okay.
Like a fully sensitive function. Without, right, that's the only thing you know about it. There is some, you can always shift points so that the most sensitive point is the origin for all the
True.
functions.
Yeah.
And the other thing is you can really always assume that a given function is fully sensitive. Because you can eliminate other coordinates. It's never, I mean, for any of these questions, you can always think you're working with a fully sensitive function. It's more or less, yeah. You can always, sensitivity is n.
I see.
Okay, then the next step is technical symmetrization.
Just to summarize, it doesn't help to think that it's like an O function.
Okay.
It's an O function. It's an easy case. How weird can it look like?
Well, I mean, I was just curious. Yeah, anyways.
So there might be a multivariable version of Markov inequality, but anyway, there's a nice technique of symmetrization to reduce this multivariate Boolean function to a polynomial with one variable. So this is the technical symmetrization. So actually for any function, you can define f of sim to be the following. It's equal to 1 over n factorial times the sum of f of s pi 1 s pi n, where pi is a permutation in Sn. So basically,
Symmetrize G, right?
yeah, I'm symmetrizing G. Yeah, but just define what's the symmetrization. Yeah. So you can think of it as you randomly permute these indices, and then you look at the expected value of f. Now, one thing that I don't want to show is that if you start with a polynomial, then after you do this step, you get a symmetric polynomial. You can actually check this. And there's a lemma. Actually, it's just very easy to prove by definition, which shows that if f is a symmetric function, then you can always write f as a polynomial composed with the Hamming weight. So here, so W is like you have W of S1 to Sn equals to the sum of Si, basically. To show this, you just expand everything, and now you can see, for example, if you have a monomial of degree S1 to the D1 times Sn to the Dn, then you can just like change the coefficient here and divide it by something like D1 plus Dn choose D1 plus Dn or something. Yep. Now I'm working over the reals. I'm not doing anything particular with the Boolean function. Okay.
Over the real, this degree is the degree over the real.
One thing, why you can compose it with a Hamming weight?
Basically, for example, if you start with f equals s1, let's say 3 variables, s1, s2, s3, then you write f equals f1 plus s1 plus s1 times s2. Then after you do a symmetrization, what you get is like s1 plus s2 plus s3 divided by 3 plus the quadratic terms. Now you can see this is kind of like the Hamming weight. The vectors with Hamming weight 1. And this is like, this only depends on the Hamming weight. It only depends on how many ones you have and how many zeros you have.
You are restricting yourself on the Boolean cube.
Yes. Now I restrict on the Boolean cube. But
Boolean
only
cube
for the last step, yeah. For the last step is, yeah, this is, this is on the Boolean cube. Okay.
So this transformation may not leave a Boolean function Boolean.
Yeah. No. So one nice thing about this symmetrization is that the degree of the fsim is equal to the degree. So if we apply it to our polynomial, our function g, then we get this thing. So basically, we only need to show that the.
Can it not be lower?
Let me see.
I don't think it can be lower.
Actually, it can.
I mean,
You can have s1 minus s2. Okay, that is less than or equal to. But anyway, it doesn't affect our proof because we only need to show.
Because you're going to have a lower bound on
Yeah.
the symmetric, right? So now it's because the symmetrization is,
zero,
at,
zero and one and
Yes.
and then, so it has to be, that's a large derivative, which then implies.
Yeah, then we can use Markov's inequality. So here I will mention what's Markov's inequality again. And if we have a polynomial p of degree d, then if we look at the L infinity norm of the first derivative on, let's say, -1 to 1, but it doesn't really matter. This is bounded by d squared times the L infinity norm of p. And this is tight for Chebyshev polynomial. Last time I gave a recursive way to define the Chebyshev polynomial, like Tn is equal, T1 equals 1, T2 equals s. Tn is equal to 2s times Tn minus 1 minus Tn minus 2. But basically, you can just say like it's the unique polynomial which maps cosine s to cosine of ns. Maybe that's a better way to understand this. So for example, if you take the derivative of this thing, you can get minus sine s times Tn prime cosine s is equal to minus n sine ns. Now when we want to look at what's the derivative of this function at 1, so you're basically taking s to be 0. So this thing is Tn prime of 1 is the limit of when s goes to 0, sine n times sine s divided by sine s. That's why you get another n here. So you get n squared. And I probably cannot give a full proof of this Markov's inequality, but basically this comes from, first you prove the Bernstein inequality, which shows that if there's a function, there's a polynomial p defined on the circle S1, then the L infinity norm of the derivative is bounded by d times the L infinity norm of this function. And then use Bernstein.
Two-variate polynomial or with a complex polynomial?
As a complex polynomial. And then use some certain technique, plug in some function like f of sine s times cosine s or something like that, and then you will be able to get this Markov's inequality. And there's also a generalization to the case derivative, but which is more complicated, and I don't think there's any easier way to prove that.
This is the Markov's brothers.
Yeah, this is proved by the elder Markov, and the generalization is proved by his brother, younger brother. And the original paper has like 110 pages long, so it's in Russian. Yeah, the original paper,
How long?
110.
110. Probably it has other results than this.
Well, no, I think they only prove it for case
It
derivative.
was a Russian paper that
The
was
Russian paper, yeah. Is it Russell and shorter? Or?
In the 19th century.
In 1889, yeah.
Maybe did they write longer papers?
Or maybe they're smaller pages. So let's see how we use Markov's inequality. So now, let's recall what's the property of our function g. So our function is fully sensitive. And so here I didn't write, but without loss of generality, we can assume g is equal to 0 at the origin. So g is equal to 0, and all the other things, sorry, I mean, if you flip only one coordinate, you get 1. So if you apply this symmetrization, again, it has this property. It goes 0. And if you flip one coordinate, it's equal to 1. And this implies that if you have the symmetrization of g equals some polynomial composed with the Hamming weight, then p of 0 is equal to 0, and p of 1 is equal to 1, right? And, but there's another very nice property that because g is a Boolean function, g is a Boolean function, so after symmetrizing, you still get the values to be between 0 and 1. So here, p of I is between 0 and 1 for integers less than or equal to n. Yeah. So Markov's inequality can be rewritten in the following way. So if we have a function, a polynomial p of degree d, where p is the range of p is in b1 to b2 for s on a1 to a2. It's just another way of stating this L infinity norm. And this is bounded by b2 minus b1 divided by a2 minus a1 times d squared. So for example, if we see from here, if p belongs to 0 and 1, then basically we get b2 equals 1, b1 equals 0, and the range is n, 0 to n. Then we immediately get the derivative. The first derivative is always bounded by d squared over n. But we know that between 0 and 1, there must be certain x such that the derivative is greater than or equal to 1. Right? There exists s in 0, 1. Then this will give you like 1 less than or equal to d squared over n. So n is just the number of variables, so it's also the sensitivity. So this will give n less than or equal to d squared. That's what we need to prove. But I was cheating a little bit. Okay.
Yeah, you're going to say this. But we know that G sim is low degree and G sim is equal to P composed of W.
Mm-hmm.
But we still need to show that P itself is low degree, right? I mean, this should be.
Oh, so here I proved it actually for the degree of P, right?
Yeah.
So this is bounded by the degree of G sim square, also bounded by the degree of F square.
You're saying the degree of.
So far I only decrease the degree.
Right. But, but still, we have this expression for G sim as P composed of W.
Mm-hmm. Oh, yeah, I need to tell you that, yeah, I didn't mention this, thank you. So I need to show that if you compose a function P with W, then the degree can only go down, right? Mm-hmm. It can go up, can only go up. Mm-hmm. Right. Mm-hmm. But I think that's kind of obvious if you verify by definition. Okay. But that's not what I was treating. Actually, if you look at this proof very carefully, you can see here we only know that Pi belongs to 0 and 1 for integers. But for Markov's inequality, we need it to be like for everything between 0 and 1. But this is not a problem. So now let's assume M is equal to the supremum of P prime of S, where S is between, let's say, 0 and n, for example. And since we know that P of I is always either 0, always between 0 and 1, okay, for any integer I. Then if we, for any s, if we look at the closest integer, so I use this notation to mean the closest integer to s, that this is bounded by the distance times the supplement of the derivative, so it's bounded by this one. And we know every integer, every real number has distance less than 1/2 to some integer, so this is bounded by m/2. So now we know that p as a function on the reals is its value falls into the range of minus m/2 to 1 plus m/2. Now if we apply the Markov's inequality, then what we get is m less than or equal to 1 plus m/2 minus negative m/2 divided by m minus, this is the same, this square. So we get 1 plus m/n this square. So if you change this a little bit, you get n less than or equal to this square times 1 plus m/n. But we know that there exists some x over m. Yeah. We know there exists some s such that the first derivative is greater than or equal to 1. So m is greater than or equal to 1. Sorry?
There exists some derivative where p of 0 and p of 1.
Because we know p of 0 is 0, p of 1 is equal to 1. So sorry. So for example, if you have a function f which takes the value 0 at 0 and it's 1. So at some point, the first derivative should be greater than or equal to 1. Okay. So now we know m is greater than or equal to 1. This is a monotone function, so this is less than or equal to 2d squared. So, okay.
There is a more general bound that tells you that if you have a polynomial that let's say has roots in some places and you have minimum distances between these roots to bound the maximum derivative. When you have the degree and the distance, the roots are separated. I mean, in general,
It's probably the same
it was
problem.
used various places which use approximation theory. There is a paper of Asbor and Christoph where they make use of
Same.
Actually, there's kind of also the Sips thing one that you only care about the function being bounded in the range -1 to 1 where the Chebyshev polynomial hits those values, and that's enough too, as that's one extreme case.
Yeah, it's the same. This is just a scaling. I mean, you can. It's just like the -1 and 1 and 0 to n. It doesn't matter. You can just scale.
So,
So this is very minor, but why did you subtract off negative m/2? Isn't p infinity bounded by 1 plus m/2?
because it can also be smaller than 0.
But p infinity is the largest it can ever be, or is that what you're...
That's good.
Instead,
Well-
they gave you intervals. They said the restatement of
Well,
between b1 and b2.
you can translate it. Well, okay. So now let's see if the same proof works for the approximate degree. So this step is basically the same, and well, here is also the same because we didn't go to the. Oh, you need to show that the approximate degree also goes down. That's not a problem. So only difference here is that you don't get p to be like 0 or 1, but instead you will get p0 is, let's see, greater than or equal to -1/3. p1 is less than or equal to 4/3. And here also everything belongs to -1/3 to 4/3.
Maybe 1/3, 2/3.
I thought it was, yeah.
You want to allow it to go close?
Oh, you are not allowed? It's not two-sided?
No,
And-
the difficult part would be when they get closer to each other, right?
I see. Oh, yeah. Well, anyway, we get some constant C1 and C2. So the only difference is when you plug in here, you get a different constant. That's why they get 6 or something. And the next thing I want to show is that actually for so last time I already mentioned that for the degree, you can find a function on 6 variables such that it's fully sensitive. So the plot sensitivity is also 6, but the degree is also only 3. So if you like recursively compose it with yourself, then you get like a degree is like 3 to the power of k, but the plot sensitivity and sensitivity are 6 to the power of k. That gives you the best separation, like log base 3 of 6. But for the approximate degree, actually the OR function will basically give the tight bound up to a constant. So, okay. Oh, this definition. And we want to show that, first of all, the degree of the OR function is equal to n. This is obvious. I'm not going to do it. And the approximate degree is like roughly, actually we only need to show this is less than constant times square root of n. And also, if you look at the plot sensitivity, it's equal to n. This is also obvious because if you look at the all zero vector, then the sensitivity is already n. So now we only need to show this part. And as you can imagine, because here in the proof we use Markov's inequality, and it's tight when you look at the Chebyshev polynomial. So here we should somehow use the Chebyshev polynomial too. So basically we want to find a function p that approximates the OR function. That's less than or equal to 1/3. And p is a real polynomial with low degree. We want to guarantee that the degree of p is like bounded by constant times root n. Sorry. L infinity. So it's like pointwisely less than or equal to 1/3 on the height. So yes. And now what we can do is we take the polynomial p to be the following. We take the Chebyshev polynomial, the 2 root n's Chebyshev polynomial. Here we look at basically the Hemingway bar, like 1 minus this. So let me write down. So it's 1 minus Sn divided by, I have to check the n plus 1 or n.
And basically, in the interval 1 to n, you wanted to stay close to 1.
Yeah.
Right? And then you wanted to rise very sharply to 0.
Yes, that's ideal. Well, anyway, we will see what this is later. So maybe it's n something. So when everything is equal to 1, this will give you, so when everything is equal to 0, this will give you 1, right? So, okay. So basically we want to show that t to root n 1. So I think it's n plus 1 minus this thing. Okay, doesn't matter. So if everything is equal to 0, then this is equal to this function value is value at n plus 1 over n. So otherwise, it's less than or equal to the value of this function at upon 1, because you can show that the Chebyshev polynomial is monotonely increasing. And now the nice property about this is that this number is always bounded by 1. Okay. Here I also need to take some constant, but I will tell you what this is in a second. So this is basically t to root n of n plus 1 over n. So we normalize it with this.
I don't get a second claim. Why do you, I see that it's bounded by 1, but it's not obvious that it's bounded by t to n of 1. A Chebyshev polynomial is not
is monotone, right?
It's not.
No,
There's many
it's
roots.
I see. So,
But that's
but
fine because
anyway, it doesn't matter. We can
Yeah.
so it's bounded by 1.
right, the input value to the Chebyshev is
Right.
bounded with one.
Yeah, it's not. You're right. It's not monotone.
But with the normalization factor also in 0 is 1. Not zero.
So we only need to show this normalization factor is large. So then if you look at the difference between this 1 and 1, then it can be very small. So
With the normalization factor.
want
I probably need to take 1 minus.
1 minus.
Yes.
One
Mhm.
minus.
Then it will give you 0 for this one. Yeah. That's why I need to look at this formula. Okay. Just 1 minus. So here I want to show two things. The first one is the Chebyshev polynomial is always bounded by 1 on minus 1 of 1, but this is kind of obvious, right? Because you can think of it as the cosine ns form I mentioned. So the second thing is that
The absolute value of it is yes.
Yeah.
absolute value. And the second thing is that if you look at the value of this at n plus 1 over n, then this is greater than or equal to 4. And this is because if you do the computation I did before, then you can see the derivative is greater than or equal to, this is not 4, so it's 4, okay. So the derivative is greater than or equal to 2 root n squared when s is greater than or equal to 1. So if you look at the difference between its value at n plus 1 over n and the value at 1, so this is greater than or equal to 1 over n times 2 root n squared, which is that is.
That's not true. At 1, the derivative is just 2 root n.
Not 1, but at some point.
At 1 is just 2 root n. No, I think the derivative is 2 root n squared.
Monotone, but actually outside, once you.
It will increase, but
No.
it starts at 2 root n, not the square of 2 root n. The square was coming because like closer to.
No.
Normalize it. It's now you live between minus 1 and 1, right?
No, I live between minus 1 and 1, yes. And in that assumption, so tk.
All the roots are between minus 1 and 1. And it's monotone outside. So if you prove that it's bigger than 4 somewhere, then it will be bigger than 4 also to the item.
Alright, how did you know that? The derivative is bigger than 2 root n squared?
Basically, I erase it right into cosine, and then you do some.
Okay.
And maybe you need to look at for the complex number, I think, also. Because when it goes out, then it might be greater than or equal to 1.
It's always what they mean complex number.
Because it means so the function is like tk of cosine s is equal to cosine ks. But if this is not in minus 1, 1, and there is the sample, but we can look at cosine for.
Actually just write the explicit form.
Oh yeah, you can write it as explicit form and then verify. Yeah. Okay. Okay, then we get this is greater than or equal to 4 or something, and this will basically tell us, well, maybe we get 3 here, so this will tell you that this is at least 3. And now let's see what this means. So if you take this to be the all 0 1, then you get just 1 minus 1, which is 0, which is the same with the OR function. Then if one of
in the
1 minus, yeah. So if you look at the absolute value of p minus 1 for all the other cases, it's bounded by 1 over this thing. So it's bounded by 1 over 3. That's what we want. So basically we show that the odd function has degree equals n, but approximate degree equals root n, and plot sensitivity equals n. And this is also the best gap between the degree and the approximate degree. And I think it would be interesting if we try to improve that.
Yeah.
No, we know we do,
Oh, we need that.
For symmetric functions,
well, symmetric function is
for
tiny.
symmetric
Yeah.
functions, yeah, they can't be more than a
Mhm.
square factor of 100.
Mhm.
I think it's unknown for.
But we don't know, and we only know that the approximate, so the degree is bounded by the block sensitivity to the Q, which I saw last time, less than or equal to the approximate degree to the power of 6, or maybe some constant. That's the best we know. Yeah. Yeah. And also, I would think it would be interesting if we can close this gap between the degree and the block sensitivity, which is what I mentioned, like log base 3 of 6. We can find a nice fully sensitive function such that the sensitivity is roughly the square of the degree. Then this can give you like maybe a quadratic gap. I don't know what's the current progress. Yeah. The best is still this.
That's the best I know. I mean, it was used, in
The red coloring,
with
right?
the rank and the case complexity. My guess is that you can do a computer search and find bigger function.
Some sort of. It's basically finding a small construction is something like integer programming. Right?
Yeah. We use just the normal equals on 3 variables. That gives you base 2 of 3.
I see.
If you need to know about Chebyshev functions, you have to try to find this polynomial separation using quantum algorithm. Try to design a quantum algorithm for solving the, Mark item finding or the OR function. And you can eventually come up with something that uses square event queries, which gives you a square event degree polynomial, which is the acceptance probability of this program. So a different perspective on it, it uses some trigonometric ideas as well.
It probably will generate something. So the standard global search algorithm probably generates something like
I don't know if it's exactly, but it looks familiar.
yeah, it might be the possibility.
Grover's search isn't Chebyshev polynomials.
Well, it's not. I mean, it's described like an iteration of Fourier transform, which is shifted, and it probably maybe it gives exactly the maybe it's the perspective. It's just
I say I always thought it was the.
Well, you always thought it's Chebyshev.
Yeah, no, but I never read it.
It makes sense because it shifts in one plane. Yeah, it looks like it's a maybe.
I mean,
So
it
when-
multiplies the angle exactly. It's cos and theta, so it should be.
Yeah, I think it is. Yeah. It's just harder because it's not working in one dimension. It works very properly.
Okay, so first I'll go back to the problem of sensitivity versus span.
Actually, maybe it gives multi-dimensional analog of Chebyshev.
I think
No, but
what
it's
it
for a
does is it
symmetric
starts with a
function.
vector with a small angle theta, and then it, by the sequence of operations, goes to cos and theta in an operation, and then the gain is just in
Yeah.
gain is n squared. I think that's.
So now I'll talk about this theorem by Kenyon and Kutin in 2004. So now I'll go back to the problem of sensitivity versus block sensitivity and show what's the best bound. So the block sensitivity of F is bounded from above by basically e over L minus 1 factorial times the sense. I will tell you what this is in a second. So the sensitivity to the power of L. So here we need a definition that the L block sensitivity is basically you are only allowed to use the block of size at most L. Block sensitivity.
But you are allowed to use them. They don't have to be disjoint.
They have to be disjoint. Yeah, they have to be disjoint. Yeah. So first we also define locally the maximum number of disjoint blocks, disjoint sensitive blocks. of size less than or equal to L. And then we define global.
And then you sum this up to get the exponential bound.
Sorry? This one?
Just sum it up over all L and you get the exponential bound.
Oh, yeah. So, yeah. So one thing to notice is that so if we take the minimum, let me see. So for example, if we in this maximum collection of these sensitive blocks, we can take every block to be minimal, right? Which means
Because you're allowing blocks of size at most L.
So yes, and then if we remove anything from it, then it will give you a sensitive bit by the following reason. So we know f of s is not equal to f of s plus bk, right? But f of s is equal to f of s plus bk plus some element y, which belongs to bk. So these two things are not, because of the minimality, so these two things are not equal, which means if you look at the function f at s plus bk, then y is a sensitive bit. So the size of bk is bounded by the sensitivity of f.
So if you were asking for a plan of this proof, you are going to set up some bipartite graph and do a double counting on the degrees from the right and from the
For
left.
fixed L.
For each fixed L.
Okay.
Because you see, you get here a connection between sensitivity with respect to the block and the sensitivity with respect to the elements in the
I see.
So basically this will give you that the S block sensitivity is equal to the block sensitivity. Because anyway, we only need to use block of size at most S of F. And if you plug in here, then you will get the best bound, which is like the block sensitivity is bounded by some constant times e to the power of s of f times root s of f. So if you can get this constant here really close to like s to the power of, I don't know, like for example, when L is equal to s, you can get this really close to s to the power of s, then maybe you can get a quadratic bound. Well, who knows? So, okay, now I'll prove this theorem.
And the difficulty is again that you have to relate the sensitivity and the block sensitivity in different vertices, because the maximum may be achieved in different vertices.
Right. Yeah. So proof. So now we take x, b1 to b, let me use a different, bt maybe, such that it so basically it maximizes the local L's block sensitivity. And now we define the new function t. Here is t. Let me call this like just b, okay? So new function ts with a collection of blocks of coordinates such that this is equal to the sum of, okay, I also need to take a sequence of weight such that W1 is greater than or equal to W2 greater than or equal to W of L. So these are basically weight depending on the size of this block. This is greater than or equal to 1. And I will tell you, I will determine what's the exact weight later. So it's basically a weighted version of some proof. So we define this to be the sum of W sub the size of B, where B is a block in this collection. So we only define on the collection of disjoint sensitive blocks for L, for X.
So this is the same set as B1 to BB?
No, it defined on any collection of
any collection of disjoint sets of sizes mod L which are
sensitive with respect to X.
Okay.
Okay. So now we can see if we have all the weights greater than or equal to 1, then this thing is greater than or equal to B, which is the L block sensitivity.
The maximum over B.
But we need all the weight to be bigger than 1. Yeah.
When you write it like this, it's not that for every B.
The maximum. Yeah.
Maximum.
And then we can take a family of disjoint minimal blocks such that this is still true. So we can also assume that. So okay, we can just take a family B such that it's minimal. Minimal means every set in this family is minimal, and also Ts of B is greater than or equal to B, which is the L block sensitivity.
Can you define this family again?
So B is a family of disjoint blocks sensitive with respect to X. Yeah. So this is bounded from below by B. So basically, we want to pick the weight carefully to. So first, we need to get some upper bound on this thing, and then we need to pick the weight carefully to minimize this quantity in order to get the best upper bound for B. So now we also define Mi to be the number of blocks of size I in this family B. Then we know that T of SB is equal to the sum of MIWI, right? This definition, where I is from 1 to L. Now we will define a new family called AK. And we will compare the function T on AK with, with this one. And by the definition, we know this is always smaller or equal to this thing. And it will give us some inequality on the MI and WI.
AK will also be a family of disjoint blocks.
Yes, it's also a family that you can, such that this function is well defined. Yeah. So basically, we pick any coordinate. So for any coordinate, K. So first of all, we assume that so K is in B for some set in this family, right?
Can we assume that the union of these elements in B is all right?
No. We can't do that. No, I don't think we can do it. Okay. And then we define AK to be the following. So AK is first you have the set B minus K union all the other subset A belongs to this family such that f of, let me write this down first, f of S plus A plus EK is not equal to f of S plus A. So basically, we are taking the set B minus K and all the other blocks in this family such that F is sensitive, such that the case coordinate is sensitive for F for at a point s plus a.
So basically, we are moving to a neighbor, to the case neighbor of this vertex x,
Mhm.
and
Yes.
looking at its block sensitivity.
And then we compare it with the previous
And
one.
then
Yeah.
obviously, if we look at its block sensitivity and want to relate it to the original family, we have to add it back.
And to this, to use this one, we have to use the sensitivity at some point. It naturally comes in. So basically, well, you will see.
But possible that the other a's, okay, so you take this a's, the a's themselves may not be sensitive blocks for this new vertex.
No, it may not be. It's sensitive block for the original vertex, but not for the new, not necessary for the new vertex. Now let's compare this t of SA. Let's be minus t of s plus. Now we are moving to the new vertex, right? And s plus ek. AK.
By AK, we just said it is not necessarily sensitive family for this vertex, so why can you apply T to it?
Let me see. No, it's sensitive for this vertex, right? Because you are only taking the sensitive blocks.
But it may not be disjoint because EK is added to.
No, they are disjoint because we take the set in the family.
No,
So
EK is added common.
No, it's added. You should write it x plus EK plus A. That's the way to write it.
s plus ek plus a.
Plus A.
Yeah. Yeah, that's better.
You shift it by A.
Mm-hmm.
Okay. So it may be a subfamily.
Mm-hmm. Yes. Let me see. I think I miswrite something. Yeah. Sorry. It's not s plus a there. S plus ek. It's quite important. Yeah. So basically, we switch the case coordinate of x and look at all the sensitive blocks with respect to this new vector, whatever you call it.
But just trying to make sure I understand. We are looking at the vertex x plus ek, and we try to shift it by A
Yes.
for any member of
Oh, we try to. Yeah, it should be by a. Yeah.
shift it by A. And this guy, x plus ek, has the same function value as x. Or we don't know that.
We don't know that.
If it was, then everything is sensitive for
Yes.
If it has the same value, then everything sensitive for its neighbor would be sensitive for it. And otherwise, it's a sensitive. So there you can gain about the sensitivity of x.
Yeah. So it basically tells you.
Minimality would imply that it should have the same value.
Sorry.
The family, since the family is minimal, if each of otherwise B would be just the set K if it was not the same value.
Right.
Yes.
That's possible.
Sorry.
That's possible. Some of these could be sizable.
Yeah, some of them can
Yes.
be sensitive.
So if B is not size 1, it will be.
Yeah. So this is greater than or equal to 0. And we can write down to see what changes here. Okay. So one thing I didn't mention is that also this is well defined on this B minus K because we take B to be minimal. Okay. So this is basically equal to, first of all, we look at the set B. So originally we have the size of B. Then the size of B decreased by 1, so it's WB minus 1 for the first term. And then we also need to add all the subsets which such that these two things are equal.
But they are all of them. It's just said that or it depends
No.
whether B is of size 1 or not.
Yeah. So it's the A in the family such that these two things are equal.
No, I mean it's possible that you have some block other than B that was sensitive for X, but it's not sensitive for X plus EK.
Yeah.
That equals F of X plus EK.
Mhm.
It's quite possible.
It's quite possible. Yes.
No, wait, why?
Yes, sorry, all right.
Why? Just look at the general function. It's possible that, I mean, so we know that if you shift X by some block, B prime in our set, it's going to flip the value. And suppose that, K is disjoint from B prime, and we pass the F of X plus EK. Even though they have the same F and X and F of X plus EK have the same value, it's not the case that B prime is necessarily still a disjoint variable.
So now what we can do next is we sum up this inequality for every K. So what we get is 0 is bounded by the sum of this difference. Something minus something, doesn't matter. So this is equal to the sum of WB minus 1 plus, so here B is the blocks that contains K. And here is this thing, I will just write it down. And for the second thing, we can use the sensitivity. Yes. Now we can see for every set A, it appears at most n times the sensitivity number of times. Because if you look at the point S plus, well, basically you have, so let's see, which point we should look at? I think it's the point S plus A. If you look at the point S plus A, then we know S plus A plus any ET where T belongs to A is not equal to F of S plus A because A is minimal. So this already gives you the size of A, that many sensitive blocks for this vertex. So the number of sensitive blocks, so this will also give you sensitive blocks for K. We know sensitivity of F is at most, where it's like S of F. So here, every block A appears at most M minus S of F times. Sorry. At most S of F minus size of A times.
Why again?
So let me write down here. Let me write down maybe. So we know that A is minimal, right, for X. So F of S plus A plus some, well, plus is the same with minus, right? Plus some ET. So for any T belongs to A, this is equal to F of S. So it's not equal to F of S plus A. So T is sensitive bit coordinate for the point X. But you can do the same thing here. Then so the total number of sensitive coordinates is A plus the number of times that this set appears. Number of times appear. But this is bounded by the sensitivity of F. So so every 8 appears at most S of F minus A times.
This is sensitive coordinate for X plus A.
S plus A. Yeah. Thanks. Okay. So now we know 0 is less than or equal to. So if you look at the first sum, it will give you the sum of I times, I is the size of the block, times mi, which is the number of blocks of size I, times wi minus 1 minus wi for I between 2 and L, plus. And for the second sum, because every, because it's, yeah. So for the second sum, again, we have mi blocks of size I times the weight of the block times, because every block appears at most S of f minus how many times I, the size of, so it's I, yeah. So basically, these are the inequalities. So what we need to do is we, as I said before, we minimize it over all the possible ways which are greater than or equal to 1. Where we maximize the sum of mi, where you can pick the size of the block, pick the numbers of blocks of size I, subject to this inequality. But also there's another thing we need to use, because we didn't really use the sensitivity except in this step. So one observation is that M1 is always at most the sensitivity of F, because Mi is the number of decision blocks of size 1. These are the sensitive coordinates. So using these things, and when you do the optimization, finally it will give you a precise bound that this is equal to, so basically this method cannot be improved. It will give you like 1 plus L, 1 over L minus 1 to the power of L minus 1 divided by L minus 1 factorial, which is essentially what we get, like E over L minus 1 factorial.
That was the bound on this sum or just the second sum?
It's the it's the whole thing.
What is S of f in this expression? What is S of f?
Good question. Subject to M1 less than or equal to S of f, yeah.
So how do we conclude that? How do we conclude the bound on the block sensitivity?
You mean the S of f to the L
Yeah.
power?
Yeah.
Oh.
That's one way to conclude it.
So
What the weights look like?
the weights looks like, didn't write down here, so it's like, let me see. It's roughly like geometric progression.
Geometric with a big constant or not, or just
It's basically with some constant, yeah. Depending on S, I think. Yeah, that's how you get S to the L.
And where did you use the bound that T was at least B?
So you remember that we need to, what we need to do is bound the block sensitivity, the L block sensitivity. And this is actually a bound on the T.
Actually what?
Bound on the T. So T is less than or equal to this. Yeah. That's why we use. So in the remaining time, I will talk about some different reformulation of this sensitivity versus block sensitivity conjecture.
We just say that L equals 2,
Uh-huh.
this is a quadratic.
Yeah, this gives quadratic. So even for k equals L equals 3, we cannot include this cubic bound yet. So, okay. So the first reformulation is that we look at the induced subgraph of hypercube q to the n. Then the original conjecture is equivalent to the following conjecture. So if you have a partition of the vertex set of q to the n into v1 and v2, then you look at the induced subgraph on v1 and v2 and look at the maximum degree. Let me call maximum degree to be delta. Delta is the maximum degree. Then the conjecture is that the maximum degree of v1, the subgraph induced on v1, and the maximum degree of the subgraph induced on v2 is greater than or equal to root n if both of them don't have size 2 to the power of n minus 1.
So any uneven partition must
Yeah.
have a large degree.
So for example, you can see if we don't have this condition, then we can just put the odd vertices into the first set, the even vertices to the second set, and there's no edge inside, right? Because for any two adjacent vertices, their parity must be different. Okay. But even if you move one vertex, you immediately get a degree like n. But you can somehow shuffle them to get like root n.
Mostly what's more striking is the fact that moving just one vertex creates such a large degree, or that this conjecture is equivalent to the sensitivity rather
Yeah,
than
it's
losses.
I'm gonna go with the latter.
Okay, so
For the strong one.
Yeah, the strong quadratic, yes.
so
So if we get
And-
any polynomial here, we'll get.
yes,
Yeah.
I will show that later. So any polynomial here will get the other one, but if you have like square here, then you don't necessarily get square for the original. There's just some other power. Okay. So first, I want to mention the best bound is due to a couple of people, Fenchuan, Graham, Freddy. Maybe they're not in the right order. Simon. They show that this function, let me call it, well, okay, they basically show a lower bound like 1/2 times log n minus some little terms, smaller terms, so log n or something like that. And the proof is very similar with Simon's proof I showed last time. And it's basically the
That's
same. Look at the,
also, and you also have the same half log,
yeah,
2n there as for the
yes.
Reason
For the
in fact,
same,
even
it's basically the
lower order
same.
term is the same.
Yeah. And the best example,
also from the same,
best example doesn't, sorry?
also from the same paper.
Yeah, it's also from this paper. And Jeff Kahn told me that this example is proved by Freddy. But anyway, they put in the same paper. So we can take V1 to be consisted of the subset, which is even. So even subset means they have even number of elements in this subset. Even subset. So first, I need to partition the coordinates into F1 union F2 union F of root n, where each Fi has size root n. So here I assume n is a perfect square, okay? Doesn't really matter. So I take V1 to be so basically think of the vertices in the hypercube as subset of 1 to n. Okay, so we only need to define for which subset we put into V1, for which subset we put into V2. So for V1, we take the even subsets containing some Fi. Union, the odd subset containing no Fi.
So you're trying to imitate the parity as much as
Yes.
possible.
Actually, the proof is also by parity, right? Kind of, and this is kind of like the certain monotone function. So
But this is the best example of
of this one.
Of the root n.
Of root n, yeah. Mm-hmm.
But
So-
root n cannot be even.
But so you can take also the Rubinstein functions and map them to get an example?
Guess so. I'm not sure if it will get root n. So what's the degree of, well, because it's like, finally we'll show that whatever bound here correspond to the relation between the degree and the sensitivity. So I'm not sure what's the degree for the Rubinstein function. Degree is probably too small. Right? Oh, it's n squared. Okay. Mm-hmm. So now B2 is just the complement of B1. And let's analyze the degrees of vertices in B1, for example, and B2 is basically the same. So for there are two cases. So if, let's say S is a vertex in B1 and it's even, then this means S must contain some Fi. So if there's another set T which is adjacent to S, then there are two cases, 1A, 1B. So the first case is like S is contained in T. So two subsets are adjacent if only if they differ by at most one element, right? So you're adding some element to S. Now this T becomes odd, and T must contain the same Fi here, but this is impossible. And the second situation is that if T contains T, S contains some T. So now T again is odd. And in order for such T to be in V1, then we need T to not contain any Fi. And let's see how many T we can have at most. So we, for example, we can have S1 just equal to, yeah, I need to remove an element of Fi such that it do not contain any subset Fi. And the best or worst, whatever you call it, the best example is like you take S1 equals just to one of those subsets. Then you can remove any of the root n elements.
S must have exactly one Fi and you destroy it by removing one element.
Not exactly. You can also have something from the others.
If it has two, then you can then.
Yeah, it must have exactly one complete Fi. Yeah. Mm-hmm. Yes. Mm-hmm. So this gives you the degrees at most root n. And okay. So. So the second case is when S is odd and S do not contain any Fi. Then, by similar reason, we only need to consider the case when T contains S, right? Because if T doesn't contain S, then it's even, and this is still true, though, so it's in F2, in V2. And this means what's the maximum? Question is what's the maximum number of the elements that can be added to S such that it contains some Fi. So the extremal case is like if we miss exactly one element from each of the sets, so you delete one element here, delete one element here, delete one element here. Then you can add any of these elements back. So it's at most root n again. And what? No. Mm-hmm. So this is basically the best example that we know.
Also, why? I mean, it may end up being balanced. How do you?
Oh, that's good. That's a very good question. It's by some very complicated inclusion exclusion, and eventually you will get one of these sets. I don't know which one. It's precisely 2 to n minus 1 plus 1, and the other set is 2 to n minus 1 minus 1. Maybe you need to assume n is odd or even. It's even.
It's not difficult.
Yes. Well, it's not difficult, but you have to write down everything and do some calculation. Yeah. And I can, well, at least for n equals 1, you can trust me, right? The empty set and 1 must be in the same thing.
So, for example, do we know in particular that there must be an extreme example of the kind where it differs exactly by 1?
I'm not sure. Yeah.
Is there also an analog of the L block sensitivity that for this, or is that not true?
For
So
the,
just
for
like,
subgraph.
Yeah, for the subgraph version.
I'm not sure because when they show the equivalence, they actually compare the sensitivity with the degree.
I see.
And they somehow need to relate the degree with the L block sensitivity. Yeah, I don't know.
Yeah, I was just curious because then, this case you mentioned of L equals 3, not knowing whether it's cubic or quadratic there. I was curious if there's an analog here about.
Yeah, maybe it's correspond to some qubit into
So it
subgraph
seems like
here.
you're losing them in something with translation anyways.
Yeah, I'll tell you the proof that they're equivalent. And maybe from there you can see how to get the right conjecture for the L block sensitivity. So, equivalence. So, I want to show that the followings are equivalent. So the first one is whenever you take a subgraph, take an into subgraph of Qn, the number of vertices is not equal to 2 to n minus 1. And, well, basically, I just copy what I wrote there. This is greater than or equal to some function of n. And this is equivalent to that for any Boolean function f. The block sensitivity, the sensitivity is greater than or equal to h of the degree of f. And finally, this is equivalent to for any Boolean function f with full degree. Oh, sorry, with full. Let me see. With the degree is equal to the number of vertices. So number of variables. Then S of f is greater than or equal to h of n. So basically, I will show these two are equivalent first by some very simple argument, and then I'll show that 1 and 3 are equivalent.
So this is Gauss-Mann linear, right?
Gauss-Mann linear, yes. Yeah, let's do it here. So let's see why 2 and 3 are equivalent. So obviously 2 implies 3. And for example, if we know 3, then we can assume that so we want to prove 2. Now we assume the degree of this Boolean function is equal to d. Now we define g of d variables such that this is equal to f of s1 to s of d. Okay, so I need to take a monomial of degree d. So without loss of generality, we can assume this is s1 times s2 times sd in the expression for f. So now we take g to be this thing. Then we know the sensitivity of f is greater than or equal to the sensitivity of g, greater than or equal to h of n. H of d, actually, yeah. Because now g satisfies the conditions in 3. And this is like what we want to get. D is just a degree of f, so it's very simple. And to show 1 and 3 are equivalent.
This is an example of why you can always assume whatever you are comparing two parameters,
maximal
that the bigger of the two is the number by the restrictions like this.
And to show 1 is 3 equivalent, so I will show 1 implies 3, and you can see from the proof that we can also reverse it to get 3 implies 1. So now we start with a graph G. We define the, let me see. Oh no, we need to show a bound for this thing. So we start with let me see. So basically, the correspondence is like if we have a function f, then it's a Boolean function f that is correspond to the partition in the following way. So v1 is equal to the set s such that p of s, p of s times the parity function is equal to 1, and v2 to be the complement of it. This is the correspondence. And here, somehow I change the Boolean function a little bit. It's no longer from 0, 1 to the n to 0, 1, but it's from 0, 1 to the n to minus 1, 1. Right? You can rewrite it, but this way is simpler.
This function is really not an issue. They took the polynomial from minus 1, 1 to the n to minus 1, 1. Then it would be just multiplying the polynomial by a monomial of all variables.
Yes. Right. But here I still use the 0, 1 to the n. Yeah. So basically, if you look at the sensitivity here of the function p, then this is correspond to this maximum degree. Why? Because when you flip the parity, then originally if there are two vertices like adjacent in V1, then it becomes like they have different values if you apply P. So this is precisely the sensitivity. So for example, if you look at the degree of the vertex in V1, then after you apply this parity function, then for any u and v which are adjacent, pu and pv must be different. So this is precisely the sensitivity. Yes. And the only thing that we need to show is that vi does not have size 2 to the power of n minus 1. So it's not a balanced partition. And the reason that this is true so here, if we know the degree is equal to the number of variables, and this is equivalent to v1 is not equal to v2. That's what I want to prove. So basically, v1 minus v2, maybe with a negative sign, I don't know, is equal to the expected value of p of s times the parity function. Maybe divided by 2 or something. But we only need to show this is not equal to 0. That's what we want to show. So I need to show this as expected value is not equal to 0. Now we can write ps as a real polynomial. So sum of some s1 to the sn to the power of something. No, power is always 1. But here you have some constant c. No. Plus some other terms. We know the degree of this.
Well, all you're going to have is non-zero correlation with the degree n term. I mean, that's if and only if.
So basically, I want to show that you will get like c times minus 1 to the n for this thing. Yeah, something like that. And to see this, we just like do the calculation. It's not so difficult. So basically, if you look at s1 times sn times minus 1 to the power of s1 times sn, and you sum up over all the x in 0, 1 to the n, then this will give you minus 1 to the n, because you can write as a product where you have basically the expected value of si times minus 1 to the power of si. So 0 times minus 1 plus 1 times minus 1 to the 1.
I think if you made it a function from minus 1, 1 to the n, it would be much simpler, because it would just, I mean, it doesn't matter to the degree, right? It doesn't matter.
Yes, it doesn't matter.
And having degree n means that the coefficient of the monomial
I
x1
see.
plus n
Because all the other.
this is the correlation.
I
All
see.
the others are
Yeah, it's
orthogonal,
much.
so it's non-zero by definition.
And in
Yes.
fact, it's probably necessary.
And then you precisely
The only
get this
non-zero
one.
term is the last term, which is sort of, I'm not sure that's what you want.
I see. Yeah. And also, if you do what Abhi said, you can just get if the degree is some other equivalence, but we don't need to use it here. So if this is less than n minus t or something, then this will correspond to the basically the Fourier transform is equal to 0 whenever the size of S is greater than m minus t or something. But for this case, it's like the Fourier transform at S equals everything is equal to 0. So, okay. And you can reverse this proof to get 3 implies 1. So the second reformulation I want to talk about is by Scott Aronson, and it's called the sensitivity of the integral lattice. Of two colorings. So basically, we have a lattice d to the d, and the two vertices are adjacent if they differ by exactly 1. So here, this is the just L2
L1
number.
or L.
Hamming distance or L2, whatever. Yeah, Ly is the same, I mean, because that integer. So now we have a two coloring, a blue and red coloring of ZD. And what we know is that first, the origin is red. And second, there exists some blue vertex on each of the coordinate axes. And we define the sensitivity of this integral lattice. First, we define locally. It's the number of white adjacent to S such that in this coloring, let me call it C, okay? So C of S is not equal to C of Y. And then we similarly define the global sensitivity to be the maximum of the local sensitivity.
There exists some vertex on each coordinate. I think. So is that starting?
There exists a blue vertex.
So sorry. So start. Just starting on the origin.
Yeah.
It doesn't say
Yeah.
anything about the point.
No,
Yeah.
It's just some vertex where only the I coordinate is not zero, which is blue. Or the I.
So the conjecture is the following. So if you look at the two coloring of ZD, then S of C, for example, let's call this C, right? There's no F here. S of c is greater than or equal to d to the power of some constant, where the constant only depend on, where this is some absolute constant. Yeah. So let's see.
What if we increase to more colors?
Oh, that's a, well, even for this one, I don't see it's solved. So if you increase to more colors, so what's the condition you want to impose here?
Oh. Oh, I see.
Maybe something like spin or slammer. Yeah, maybe we can say on every coordinate has like blue and green vertices, but somehow it's not very symmetric though. I don't know. Yeah. So first I can show why this is equivalent to the original conjecture. So remember this is equivalent to block sensitivity.
So here we have N is D and coloring is
Yeah. Well, basically we want to start from the blocks and then define the work on this hypercube and again translate into this coloring.
Yeah, I'm just saying N will be D, the number of variables.
Yeah, and D is no, D is the block sensitivity.
Okay,
Yes.
sorry, yeah.
Let me write into this way. I can compare these two things. So now what we do is we start from f of s, where this gives you the block sensitivity. And the blocks are B1 to BB, for example. And well, lots of generality, we can assume these are the first, this many coordinates. Okay. And we have f of s plus bi is not equal to f of s. And we can also assume s is equal to 0. I mean, it doesn't matter. Just for simplicity.
And B is D, so you're going to B will be D.
B will be, yeah, B will be D. Maybe it's better to just put it D here. So what we can do is we look at the hypercube. Then we start with the point 0, 0, 0, the origin, and then we go to some bi, and then we can get back. So we define the closed work wi. Starting from 0, it goes to bi, where I is the same I here, and then you eventually will return to 0. So assume the maybe wi of length. Assume the length of this work is equal to wi, and the work can be described as v from basically 0 wi to this hypercube, but you can extend it to a periodic function. So it's from z to 0, 1 to the n. Let me see. 0, 1 to the n. Yes. Of period wi. We call it maybe phi. And now we define the new mapping from z to the power of v to d. Okay, but here this is z to 0, 1. Okay, z to the power of d to 0, 1 to the n. by the following. So basically, we map S1 to SD to phi1 S1 to phi d SD. S is not a good thing to do because we need to use the origin. But okay, well, anyway, we assume the origin is 0. So we map the others to 0. And here, this is not to n. It's actually to the basically the size of this block. We can do it just inside this bi-dimensional hypercube. I want to map this. This map is from GD to 0, 1 to the n. So I map this thing to 0, 1 to the B1, size of B1, to 0, 1 to the size of BD, and so on. And for all the remaining things, we map it to 0. Then if you compose the polynomial, let me see. Yeah, if you compose the Boolean function f with phi, so if you have everything equal to 0, it's just equal to f of 0, which is like 0. And for certain, there exists certain yk in the case coordinate, such that this is equal to f of 0, and here you will get the block bk 0, and this is not equal to this one, so it's equal to 1, and this corresponds to the red and blue coloring. And yeah. Actually, so I made a mistake. So these two are not equivalent. We don't know if we can prove this conjecture from the sensitivity versus block sensitivity conjecture. We can only show that this conjecture will imply this conjecture. We don't know if they're equivalent. And the best example that we know about this conjecture, the first.
Suppose just to finish the reduction, suppose somebody gives us some vertex somewhere in the lattice which has high sensitivity. Why does it mean that the vertex? So you have to prove that. I mean, I guess the map does.
I see. So first, I need to pick the. I see. Yeah, you still need to complete the proof. So now we know the sensitivity of f composed phi is greater than or equal to d to the power of some constant, right?
I guess any number you put there is supposed to be at the same number.
Yeah, it's the same thing. Yeah. And now we know the sensitivity of f is also greater than or equal to this thing. Because when you compose it with another function, you can only go down.
Well, they live in different places. I mean, the one lives on the lattice and the other lives in the Boolean cube.
Right.
So it's just that it's a preserving, it's an edge preserving matrix with graphs. That's it's homomorphic.
Yeah. Well, I know this like two different notations, but somehow you can get this. Yeah. Okay. So the best example is by Mina Bopona. And this was actually from a mass overflow discussion, which Andy was also involved in. And then she get some answer and then publish a paper. Right. So what you can get is like you can find the coloring such that.
You have a paper with me?
No, I was observing something else.
Okay.
Discussion, but she took us into some research project.
Yeah.
You know, the discussion is under the same thread, and yeah. So you can get like d is equal to 2s squared minus s. So basically, what this means is that there exists a coloring of g to the power of 2s squared minus s, such that the sensitivity of this coloring is equal to S.
So the whole point is that it's slightly better than the Rubinstein example by a factor of 4 or something.
But
I mean, otherwise we could get this
it's
example
quite.
we could take Rubinstein example and map it to the integer Russell side, so then we would get probably.
I see.
somehow
Yeah, this is probably the very similar thing.
Okay.
I don't know if it's exactly the same with Rubinstein's function. Yes. So basically what we do is we partition the coordinates into, let's say, Sij, where I is between 1 to S, j is between 1 and 2s minus 1. And we consider the so-called slice to be the following. So it's all the SIs such that there exists certain A and B with SAB is equal to 3 and let's say AT is equal to 0 for any T which is not equal to B. So it's basically you have S by 2s minus 1 transpose. Then if you look at each row, so if this coordinate is equal to 3 and all the other numbers are equal to 0, then this defines you the slice called SAB. Then the coloring is just if a point belongs to one of the slices, then you color it blue, and if it doesn't belong to any slice, you color it red. Obviously, the origin is red, right? Yeah, because every coordinate is equal to 0. Let's just finish it here. So first, the origin. So is everybody clear with how to color this vertices? Okay. Then the second thing is I want to show that there exists a vertex in every coordinate axis such that it's blue. And this is obvious because you can just take some coordinates to be 3. Take this coordinate to be 3, everything else to be 0. And this is the blue vertex. Okay. 0, 0, 3. So the only thing we need to verify is we want to show that the sensitivity is equal to S, sensitivity of this coloring. Let me just write down what the coloring is. So C is, so it's blue if S belongs to some slice SAP. There is red otherwise. Okay. I want to show the sensitivities at most S. So if we look at the blue sensitivity, so now we take a blue vertex, which means there should be one row satisfy this property. Then now you can see if you change anything other than the elements on this row, you cannot change the color. Right? So the only thing you can change is here, so it's at most S. And for the red sensitivity, so here is the property that we can verify. So every red vertex is adjacent to at most. Let me see. So for any fixed A, every red vertex is adjacent to at most one slice SAB. So if this is true, you imply that the red sensitivity is at most A. With at most the number of possible choices for A is also S. And to see why this is true, just notice that if something is adjacent to this slice, then here you should have like either 2 or 4 or 3, but then you cannot get to 0. So you cannot be adjacent to two slices at the same time. Okay, so this will tell you the red sensitivity is also at most S. The next example, and I'm not sure whether it follows from the Rubinstein, but they look really similar. So yeah, but all these things are similar because we don't really.
I think that it's a better constant than Rubinstein.
Yeah, maybe, but also there might be better construction than
Rubinstein. It's the same constant. It's n squared then over 2.
There have been small improvements to the constant for Rubinstein recently, and I think that Einstein bias had this paper that sort of said that among some kind of relatively narrow family in which Rubinsteins, lives, they know this is the best constant.
Yeah, I think they improved this 1/2 from Rubinstein to 2/3 or something. Yeah. Also, one thing that I forgot to mention is for this example, if you take the family to be defined on using the parity function together with some subset, some kind of like down-closed family, actually it's upper set closed family, which means if a set is in this family, then anything containing it must be also in the family. Yeah, it's a monotone function. Yeah, then this square root of n is the best we can do.
But that
I think it's the same with the monotone function. Yeah. I see, but in the paper they proved this result. I think they are not really aware of what's going on in computer science.
No,
so
they use Simon's result.
Oh, they know it?
So
they just like copy the proof. I see.
You are talking about the Chung-Gram purity, yeah.
I see, but then their proof is almost identical.
Yeah.
I see. Anyway, I think I will finish the talk here. Thanks for coming.